Kate is recording. Kate's an assistant professor there. Got a PhD in 2013 from the Ohio State University. You have to say the Ohio State University. And went on to a postdoc at Penn State and has been at the University of Wisconsin since 2022. She's an observational astronomer. She studies supermassive black holes and usually the environments near the supermassive black holes. She does reverberation maps. We're going to talk about all this stuff and high cadence spectroscopy. Welcome, Kate, and you can take it away. We can hear you and see you very well. So it's
okay, great. Let me go ahead and get my screen shared here. Did that work? Can you see? No, it did not work. Hold on.
It didn't.
There we go. Okay, how about that?
Yeah, perfect.
All right, there we go. Okay, thank you for having me here today. Yeah, I go by Kate, and I am going to talk to you about my a wide range of things today that we've been studying with a program called the SDSS-V Black Hole Mapper program. So to get started, we'll talk a little bit about supermassive black holes, quasars, and active galactic nuclei, and then we'll talk more specifically about my research and the research of the group that I've been working with for a while. So when we talk about supermassive black holes, we're talking about black holes that are hundreds of thousands to billions of solar masses. So imagine taking a billion suns and squishing them into something the size of our solar system, and that gives you a supermassive black hole. These exist at the centers of pretty much all massive galaxies, and they are the power sources behind active galactic nuclei and quasars. So these three images that I have at the bottom of this slide are actually just some of my favorite supermassive black hole images. Over here to the left, this is an actual image showing the shadow or very close into the event horizon of a supermassive black hole in a galaxy known as M87. And this was from the Event Horizon Telescope. It made the front page of the New York Times a few years ago, so it's a pretty well-known image. This middle image actually is an image showing the quasar that hosts the largest black hole that we've ever measured. It's TON 618, and it's about 66 billion solar masses. So that is the current record holder for actual supermassive black hole measurements. And then I also like to show the simulation of a supermassive black hole from the movie Interstellar, because this simulation was actually done using pretty physically accurate models, and it shows the gravitational lensing and effects where you can see the black hole's accretion disk, and the black hole lenses a lot of that light, and it's just a really cool image. So, so we're going to be talking a lot about supermassive black holes and their masses. So the Milky Way has a supermassive black hole. It's about 4 million solar masses, and it's called Sagittarius A star. And it's close enough to us, because we live in the Milky Way, it's close enough that we can actually see the stars moving around it. So this image actually shows a combined X-ray and infrared image of the very center of our galaxy. And if you zoom in really close, you can see there's an X-ray source at the very center. And that X-ray source is a supermassive black hole that is occasionally accreting material. Now, the way that we know that it's actually a black hole, however, is actually by tracking the motion of stars around it. So I'm going to play this video a few times in a row. This is a time-lapse series of a whole bunch of infrared images of the center of our galaxy. So you can see at the top left, we have the year that the observations were taken. These are infrared measurements of stars at the center of the Milky Way. And this plus sign denotes the location of the center of our galaxy. So this is Sagittarius A star. And so you can see that over very long periods, we can track the orbits of these stars. In particular, this is the real, really cool one. But if you track the motion of the stars at the center of our galaxy, you can see that they all are orbiting this apparently empty region in space. They all have a common focus in their orbit, and they all kind of bend around this seemingly empty region in space. And that is where our supermassive black hole lives. That is Sagittarius A star. And by using these orbits and the velocities of these stars and the size of their orbits that we can measure from these images, you can determine how much mass is enclosed in those orbits. And it turns out that there's inside that empty looking region of space, there's around 4 million solar masses of stuff having a gravitational effect that affects the orbits of these stars. And so we determine, we have upper limits on the size of that region from these images and the fact that there's nothing there in the optical. And the only thing that can be in there that is that massive is a supermassive black hole. So the Milky Way's black hole is not really pulling in very much gas. Most of our evidence that it exists comes from the orbits of these stars that we can track. But we also occasionally see material wander too close and get pulled in. We see like clouds of gas, for example, that wander a little bit too close to the black hole. And when that happens, we will see like flares of X-rays as that material falls onto the black hole and gets eaten. But generally, we consider our black hole in the Milky Way to be what we call a quiescent black hole, where it doesn't have a constant supply of material falling into it. Now, it turns out that we have a supermassive black hole that we can measure in our own galaxy, but it also turns out that other galaxies have them too. Now, these other galaxies are too far away for us to be able to track the individual stars like we did for the Milky Way, but we can actually use the orbits of large groups of stars and also like large chunks of gas, large populations of gas at the center of these galaxies to figure it out. So if we have sufficient resolution, we can resolve the very, very centers of these galaxies close enough in, we can get the velocities and the distances of these large populations of stars and galaxies to determine how much mass is inside there. And it turns out when you do that, in pretty much every galaxy, you find a supermassive black hole. You find a black hole that is hundreds of thousands to billions of solar masses. Now, even though we have this evidence based on velocities and orbits of stars and gas, there's a lot of people who like more direct evidence. And so since 2019, we now have direct evidence in the form of images taken by the Event Horizon Telescope of a couple of our supermassive black holes. We have one for a galaxy called M87, which is shown here. And we also have one of these images for our own Milky Way supermassive black hole as well. And these images were made, so the resolution required to make these images is far beyond what single telescopes can do on their own. And so the Event Horizon Telescope is a network of telescopes scattered across the Earth that are used in concert with one another to improve the resolution so that we can resolve these really teeny tiny scales that we can't do with individual telescopes. So just as a comparison, these are the two images that we have for supermassive black holes from the EHT. And so this is the accreting matter around the Milky Way's supermassive black hole. And just for scale, you can see where the sun would be and where Mercury's orbit would be. And this shadow in the middle is about the size of the event horizon of the black hole. And in comparison, you can see just how ginormous the supermassive black hole in M87 is, where the event horizon is on the order of the size of Pluto's orbit. So it's a much bigger supermassive black hole. These things are really enormous and have the potential to really generate a lot of energy. So it turns out that looking at a lot of nearby quiescent galaxies and measuring their black holes, we've determined that there are strong correlations between various properties of the galaxies that the black holes live in and the mass of the supermassive black hole at the center. So for example, this plot is showing the black hole mass measured again through like the motion of stars or gas as a function of the mass of the bulge of the galaxy, so the inner sort of spherical part of a galaxy that the black hole lives in. And there's a number of these correlations with different galaxy properties, but it turns out that the black holes, even though they're billions of solar masses, they are still much smaller in mass than the rest of the galaxy that they live in. They aren't necessarily large enough to have to impact the size of the galaxy. But it turns out that they do. They seem to, at least. And so this is brought up the idea that galaxies and their supermassive black holes evolve in a way that's somehow connected. So in order to understand how galaxies are formed and how they evolve, we need to understand how their central supermassive black holes grow and what the mode of interaction is between the supermassive black holes and their host galaxy. So in order to do this, we need to measure black hole masses and galaxy properties in as many galaxies as possible. So we can, put these measurements into our theories of how galaxies form and evolve. And so my research is focused on the supermassive black hole side of that puzzle for the most part. So my research is measuring the masses of these supermassive black holes and trying to measure these masses in as many galaxies across the observable universe as we can. So how do we do this? So I told you already that in nearby galaxies, in nearby quiescent galaxies, we can use the motion of stars and gas that's very close in to the central black hole to measure the black hole mass here. For galaxies outside the nearby universe, however, we don't have the resolution to do that. If we go beyond even the nearest, say, 200 or 300 galaxies, our current instrumentation is not able to give us a high enough resolution to make these measurements. And so we need another way to measure black hole masses. And so the way that we do this is using active galactic nuclei. So active galactic nuclei are objects where, so originally the name was actually given just when the center of a galaxy was unusually bright. They called it an active galactic nucleus or an active galaxy. Quasars are active galaxies. They're just the most luminous examples of active galaxies. So the idea is that looking at this galaxy here as an example, this is actually M87, which is the same one that I was showing you before. You can see it has a really bright center. And in most cases, actually, the very compact nucleus in these objects is brighter than the entire rest of the galaxy combined. So you have billions and billions of stars that are being outshone by this tiny little point source at the center of the galaxy. And so we call these active galaxies or quasars. And what's happening in there is that you have a supermassive black hole, okay, at the very center. And that supermassive black hole has an accretion disk. So it has a disk of material that's falling into the black hole. And that material heats up. It gets very, very hot and very, very bright, very luminous. We see this light across the entire electromagnetic spectrum, all the way from X-rays, all the way out to the radio. And essentially, when the black hole has a steady supply of food, or steady enough at least, it can sustain this accretion disk for very long periods of time. And we see them as, they produce, this accretion produces enough energy that we can see these across the entire observable universe pretty much. So we're going to talk a lot about the inner regions of AGN and quasars here. So here's kind of a little cartoon of what I want everybody to kind of visualize when we're talking about these regions. So at the very center, again, we have this supermassive black hole. We're not going to worry too much about the event horizon or gas coronas here. Mainly what I'm going to talk about is the accretion disk, which is surrounding the black hole. Excuse me. And a little bit beyond the inner accretion disk, we have a region filled with fast-moving gas that's called the broadline region. And I'll come back to that in just a second. But we have this fast-moving gas that produces broad emission lines in quasar spectra, known as the broadline region. There's also a number of other important characteristics of AGN here. Farther out, we have slower moving gas, these big clouds of gas that are not moving very fast, and so they produce narrow emission lines. AGN are also characterized by often having these strong jets of material spewing out perpendicular to the accretion disk. And we often also consider that there's some sort of dusty medium surrounding this inner system that can affect the way that we view it depending on the angle that we are seeing the AGN. So for example, if we're looking at if our view happens to be looking through this dusty medium, we don't see the inner regions here. We only see the narrow emission lines, these regions that are farther out. Whereas if our angle is looking through, like kind of the donut hole, if you will, then we see the broadline region and we get more light coming from the accretion disk. So when you look at a spectrum of an AGN or a quasar, there are a number of distinct features that correspond to these various regions within an AGN. So underneath the entire spectrum, so this is an example of this is actually a composite quasar spectrum, including thousands of quasars in the ultraviolet and optical. And so you can see that there's what we call the continuum emission underneath the entire spectrum that's coming from the accretion disk. We also have these broad emission lines here that are coming from the broadline region. So this fast moving gas that's a little bit farther out. And then we have our narrow emission lines in some cases as well that are coming from that gas that's even farther out and not moving as fast. And so the most important parts for our purposes today are the continuum, again, which is coming from the accretion disk, like inner regions, and the broad emission lines, which are coming from the broadline region a little farther out. So assuming that the motion of the gas in the broadline region is dominated by the gravity of the black hole, we can actually use the broadline region gas to measure black hole masses. So if we know the velocity of the gas, the distance of the gas from the black hole, and the distribution or behavior of the gas, then we can measure the black hole mass. So again, using sort of pretty simple virial arguments, we can determine how much mass is in there if we essentially know the orbit of the gas in the broadline region. So let's talk about how we get each of these things. The first is the most straightforward because the broad emission lines are Doppler broadened, which means that broader emission lines will show you gas that's moving at higher velocities. So if we can take a spectrum and measure the width of some of the broad emission lines in this spectrum, that can give us a measurement of the velocity dispersion of the gas that we're seeing in the broadline region. All right, so that gives us our V that we need. The R and the F are a little bit problematic, however. We generally cannot resolve the broadline region in AGN. There are a few examples where people have used interferometry to measure the broadline region in some nearby AGN. But in general, the broadline region is on the order of micro arc seconds in angular extent, and that's not resolvable with most of our current technology. So we can't just look at it and see how far away the gas is from the black hole. And so in order to measure this R, the radius of the broadline region, we need to find some other way to do that. And so we do that using a technique called reverberation mapping. The way reverberation mapping works is that if you monitor an AGN over a long period of time, you will find that it is variable. And you can see that the accretion disk around the AGN at the very center here, you'll see some kind of signal, some kind of variability signal coming from the accretion disk. That signal then propagates out to the broadline region, which is farther out. There's a time delay between when we receive the signals from the continuum and when we receive the echoing signals from the broadline region. And if you can measure the delay between the signals that arrive from the accretion disk or the continuum and the broadline region, then you can get the distance between those two regions. So over here on the right is just a little cartoon showing that, okay, so we have sunlight coming from the inner parts of the accretion disk, which we're showing in this top panel as the continuum, and some light coming from the broadline region farther out, which is coming from, in this case, the H beta broad emission line. And we're showing the brightness as a function of time. And so you can see that we see variability in both of these, in light coming from both of these regions, but there's a short time delay between when we receive these signals. And so the idea of reverberation mapping is that if you can measure this time delay, then you can measure the distance between the two regions because the delay between the signals is just due to light travel time. So you can actually use reverberation mapping at various different wavelengths to explore different regions of the AGN. So for example, people use X-ray reverberation mapping. X-rays are thought to come from the very inner edge of the accretion disk and also the corona above the black hole. And so you can use X-ray reverberation mapping to probe the very inner regions. You can also go all the way out and use infrared reverberation mapping to actually probe the dust, the dusty torus that is surrounding the AGN. And so my work is focused mostly on optical reverberation mapping and some UV as well, where we use the broadline region and the continuum light to measure the structures in the broadline region and in the accretion disk of the AGN. So here's what a real data set looks like for a reverberation mapping monitoring campaign. So on the top panel, these are light curves. So it's the brightness of the light as a function of time. For the continuum emission on the top, and for, again, we're showing the H beta broad emission line on the bottom here. And so this is actually data from my PhD thesis a while ago now. But we have 180 days of monitoring of an AGN called Mercurian 335. And so you can kind of see there's some common features in these light curves. And so the time delay between these two signals is roughly, for this object, roughly, I don't know, 30 days or so. But between the peaks, you can see in these two light curves. So if we can measure that time delay, we then get a radius of the broadline region, which we can then feed into our black hole mass equation and combine with our velocities to measure black hole masses. Now, the last part of this equation is this factor F. This F factor depends on what the broadline region structure is like and what our angle of viewing of the system is. So, what the gas inside the broadline region is doing. This is also, unfortunately, unknown in most cases because, again, we cannot resolve this region in most cases. And so we actually can use reverberation mapping to get an idea of what's going on by fitting models to reverberation mapping data and coming up with geometric and kinematic models of the broadline region as well. We normally do this using a technique called velocity resolved reverberation mapping, where rather when we're considering a broad emission line, such as H beta that I've mentioned before, rather than considering the light in the entire emission line, we consider the light at various different locations within that emission line, which corresponds to gas moving at different velocities. So for example, here I'm showing the H beta emission line on the top panel, divided up into just 8 different velocity bins. And we then measure the light curves within each of those bins and measure the time delay between the light and the continuum light. And you can see that the blue side, the bluer side of the line is responding at longer time delays than the red side of the line. And that's actually an indicator of inflowing gas. And so we can use velocity resolved reverberation mapping to get an idea of what the gas is doing. And if we have really nice data sets, we can fit these models that I'm showing here on the right, where we get an idea of what the geometry looks like, what angle we're viewing the system, and a slew of other details that we don't get when we just measure, sort of lump everything together. So in practice, reverberation mapping is very observationally intensive. You need high signal to noise data so that you can disentangle your emission lines from noise. You need flux measurements that are calibrated to within a few percent accuracy because we're relying entirely on the variability to measure these signals. And so we need to be really confident that the variability we're seeing is real variability of the AGN and not just variability due to systematics in uncertainties in our calibrations. You need very long time baselines compared to the expected lag. You need time to observe something happen to the AGN. They don't always vary in a nice way, unfortunately. And so you need time to measure interesting variability and then also have time to get the response below. And you also need high time sampling relative to the expected lag. If you're thinking you're going to have a time lag on the order of a few days, then you need to be observing a day or every day or less. Otherwise, you won't be able to resolve that signal. So it's a very observationally intensive process. This one measurement that I'm showing here took 180 days of daily observations, followed by 1 to 2 years of concerted graduate student effort. So it's a lot of data and a lot of work just to get even a few measurements out. Now, luckily, as measurements, so starting in like the 80s and 90s is when people started to really start reverberation mapping in earnest. And over the years, we compiled around 60 measurements or so that were used to determine that there's actually a very tight correlation between the luminosity of an AGN and the size of its broadline region. So the more luminous an AGN, the larger the broadline region it has. And this correlation is very handy because now all you need is a luminosity measurement, and you can estimate the broadline region size by applying this relationship. You can then combine that with a single measurement of the width of the emission line, and that allows you to measure a black hole mass from a single spectrum instead of having to take hundreds of spectra in order to get one good reverberation mapping result. So this has been really widely used to measure black hole masses in AGN across the entire observable universe. This is both good and worrisome because this relationship is being applied, when you see in the news, for example, that people with JWST have found a supermassive black hole at a redshift of 8, which is less than 1 billion years after the Big Bang. This causes a lot of difficulties in theories for how supermassive black holes form. But those measurements are all made off of a relationship that's calibrated on using local active galactic nuclei. And so without reverberation mapping, we wouldn't be able to measure those black hole masses. And so we need to make sure that this relationship is calibrated really well and that we understand which AGN, if not all, that it can be applied to. So these days, there's kind of 2 different modes of reverberation mapping that are happening. We have what I'm kind of calling like single object campaigns, where you have usually like a modest sized telescope where you're able to get enough time to really observe very frequently over maybe one observing season. And you get these really high signal to noise spectra. You get really high signal to noise light curves. You can sometimes do velocity resolved reverberation mapping, and often just kind of get a lot of detail and a lot of information about single AGN. Now, just due to observational constraints, these types of campaigns are usually limited to fairly local, low luminosity AGN, just because as you move farther away, they get to be higher luminosity, their time lags get longer. There's also time dilation effects from their redshift. And so you end up with really long time lags that take years and years and years to measure. And so usually it's very difficult to get enough telescope time to do that. And so these single object campaigns tend to just focus on nearby objects where we can get tons of information and investigate nearby. But recently, we've also started running some larger scale campaigns using multi-object spectrographs. So these types of reverberation mapping efforts are carried out on survey telescopes over several years. They are more low precision. We don't tend to get quite as high signal to noise or quite as frequent observations, but we can observe hundreds of AGN at a time. I was showing you my SDSS plate back here. So here's another image of what an SDSS plate looks like. There are 1,000 holes in this plate that feed into each hole is at a location of an object. And so we can observe 1,000 objects at the same time with this spectrograph. And so we can do statistical analyses, and we can also start to look at AGN that are much farther away. We can usually, with big surveys that are already planned to run over many years, we can also get a time baseline that is long enough to detect longer lags. And so that's what these multi-object campaigns are aiming to do. So ever since roughly around 2014, when it began, I've been involved in a project called the Sloan Digital Sky Survey Reverberation Mapping Project. So in 2014, we started monitoring 849 quasars with SDSS. This project continued through 2020, although we are actually still monitoring this field as a part of the Sloan 5 program, which is happening now, and I'll come back to that later. But the SDSS reverberation mapping project itself had 8 years of spectra, more than 10 years of photometry on this field. And so our goal was to measure black hole masses in as many different kinds, in as many AGN with different properties and luminosities as we possibly could. And so with those 8 years of data, we were actually able to make more than 300 black hole mass measurements. This plot here shows these measurements. So all of the colored measurements come from our SDSS program. The gray points are all of the other reverberation mapped AGN that had been done prior to the SDSS program. So you can see most of them are very, very nearby. There was a handful that were done on a really long running program before, but we were able to fill in a huge chunk of space in this redshift black hole mass space here. And we're now measuring black hole masses in quasars that are 10 billion light years away. So previously at redshifts of greater than 0.3, there were only 15 measurements total, and now we have more than 300 of them. So just with the first 8 years of data, we were able to measure a whole lot of black hole masses and using reverberation mapping, just using these multi-object spectrographs. Now, one thing that came out of this that was a little bit concerning was now when we started looking at the radius luminosity relationship that everybody is using to measure black hole masses, we start adding highly accreting or higher redshift quasars. We now find a lot of objects that don't seem to fall very close to this relation at all. And it turns out that there is a relationship between the accretion properties of AGN and where they fall on the radius luminosity relationship. And so we are now trying to figure out how we can correct for this. So the radius luminosity relationship is actually very likely to depend on the connection between the light that's received in the ultraviolet and the light that's received in the optical, which is actually what we're measuring. And so one of my graduate students at UW-Madison is currently working on trying to come up with a correction to the radius luminosity relationship based on the ultraviolet and optical shape of their spectral energy distribution. So these plots show, this is just the radius luminosity relationship. This bottom one shows a few different spectral energy distributions for quasars that have different accretion rates. And you can see that in the UV and optical, the accretion rate very heavily influences the shape of this curve. And so we think that that might be causing a lot of this scatter on the radius luminosity relationship. And so we're working on trying to correct this so that the relationship is correctly applied to all of the quasars that we're using to measure it. So this project yielded more than 34 publications. Many of them were reverberation mapping related, but we also did studies of host galaxies, about absorption-line quasars, emission lines of quasars, just general quasar variability, a whole lot of things. So there's a whole lot out there and a whole lot you can do with a data set like this. And so we view this as pretty highly successful. And so as a result, we have an expanded program that's running right now as a part of the Sloan 5, SDSS-V program. This is just a little schematic showing where the telescopes for Sloan 5 are located. But we have what's called the Black Hole Mapper Reverberation Mapping Project that's observing 3 fields from the Northern Hemisphere up here from Apache Point Observatory, and 2 more fields from the Las Cumbres Observatory in the Southern Hemisphere. And so now we are aiming to measure masses for more like 1,000 quasars. And we've been observing these fields since the fall, and we're hoping to just expand upon what we did with the previous SDSS program and measure some more. Now, I don't have any reverberation mapping results to show you yet, really, because we are still building up our time baseline of observations. I'm expecting the first sort of large-scale reverberation results from this program to come out this fall, actually. But here's a few spectra of some of the quasars that we are observing. And I wanted to highlight just a few of the sort of first results that have come out of the Black Hole Mapper program. One of which, I'm going to start this video, one of which is a quasar that we found that had really, really strange behavior in its broadline region. So the idea here is if you watch this video, you can see the H beta emission line at each epoch compared to the median profile of H beta. And right now it's not doing very much, but later on in the campaign, you can see that the H beta emission line shows some unusual behavior in that it shifts off from its nominal center. Both the shape and the location of the H beta line change. There it goes. And we don't normally see behavior this dramatic. And so this is one of our brighter SDSS reverberation mapping quasars. And so we were able to do some more in-depth analysis and determine that, yes, the blue shift of this H beta line is changing throughout time. So is the width, and so is, well, these are both just different measures of its width, but also so is the flux. And it turns out that we think this is some combination of like very weird broadline region structure that we haven't really observed before. And if we look at it even in more detail, we actually have a nice enough data set that we were able to fit geometric and kinematic models to the broadline region. So here we're showing geometric models of the broadline region gas, as well as you can see color-coded by what the gas is doing. And we're looking at maps of the time delay as a function of gas velocity across the emission line. And you can see that in different emission lines, we see different structures and different gas behavior. So we were able to do kind of a really detailed modeling of this reverberation mapping data and in a much higher redshift quasar than we've ever been able to do before. Just from this, now we have 15 years of monitoring photometrically and 10 plus years spectroscopically. So we've been able to do some really cool stuff with this field. We have a couple of graduate students working on photometric observations. So most of SDSS SDSS is providing us with spectroscopy, but we are also monitoring these quasars with a wide range of telescopes that we have either institutional access to or we can access through public facilities. And so as a part of the Black Hole Mapper program, we have a pretty substantial photometric observing program that is being led by my group up at UW-Madison, my student Teddy, as well as a grad student at the University of Illinois named Zach Stone. And so we expect to be publishing those light curves as well sometime in the next year or so. Now, so a little bit off topic, but not necessarily reverberation mapping. A lot of our work right now, while we're waiting for our time baselines to get long enough to do reverberation mapping, we've been doing sort of some ancillary science with the Black Hole Mapper data. And one of the things that we've been looking at are quasar winds. So when you look at a subset of quasars, roughly 10 to 20% of them, have these really broad absorption lines in their spectra. You can see here, this is just an example of one of them. A normal quasar spectrum has these emission lines in it, but doesn't have these really gigantic absorption features. These absorption features come from fast-moving outflows that are launched off of the quasar accretion disks. And it turns out that these outflows are also variable. So when we have time series spectra of BAL quasars, or broad absorption line quasars, we can actually use that variability to learn about the physical conditions within these outflows that are being launched. And the reason why we're interested in these outflows is because they are potentially energetic enough that they could travel beyond just the central regions of the host galaxy and provide significant, what we call feedback to the host galaxies that they live in. So if these are energetic enough, they can actually significantly affect star formation in the galaxies that they live in, which is one way that AGN can interact with their host galaxies. So we want to know more about these outflows. And so we do this by looking at their broad absorption lines. Broad absorption lines are variable. Here is a couple of examples of variable broad absorption lines. You can see these gray regions here. These are just two different observations plotted together. So you can see these absorption features vary quite a bit in strength and also in shape, and some of them can disappear entirely at times. And most studies of broad absorption lines in the past have not had very high cadence data. They've had, maybe 3 to 5 spectra that covering a time range of, maybe 5 years or 10 years or so. They're all spread out by several years. But we now have roughly 90 Bal quasars in our SDSS-RM sample, where we have, 180 spectra that are spread over a decade. So we can explore timescales down to a few days, but also up to on the order of a decade. And so this is really a unique data set that we just haven't had access to before to study. And so we have a team of, I have a team of 4 students at, well, I guess 3 now, Robert's gone, but 3 students at UW-Madison, plus another couple students at other collaboration institutions who are looking at Bal quasars in our SDSS-RM sample. So here's another just example of one of our quasars here. You can see the broad absorption features here underneath the carbon-4 emission line. And so we are doing a lot of work to characterize the variability of these broad absorption lines and use that variability to extract information about the physical conditions that these BALs exist in. So what, how they're launched, how they're produced, whether they provide feedback to their hosts or not. So we have 92 of them in our original sample, and we expect to find roughly 100 more in the fields that we've just started monitoring. So we haven't gotten to that yet, but we have quite a few here. So it's really just a really cool data set that nobody's ever had before. And so we're doing a lot of studies on these broad absorption line quasars with it. So one of the cool things I wanted to highlight, one of my students and I published a paper last year, is one of our broad absorption line quasars was doing some interesting things. So here at the top left, you can see the quasar spectrum. You can see zoomed into the carbon-4 region here. We have a carbon-4 broad emission line. And there's also this very broad absorption feature that we've got labeled trough A here. And if we track the strength of that absorption feature and the average speed of the outflowing gas, so like how fast this gas is moving, you can see that it's pretty variable in strength. That's normal. That's not unexpected. What we didn't expect to find was that its average speed is also increasing, so becoming more negative. In this case, negative velocities indicate blue shifted material that's moving toward us. So it's moving faster over our monitoring period. And before, we had written a paper on this back in 2015, where we just had the first year of data here. And so we had no idea that this BAL was moving. And when I had my student look at the whole 8-year set, all of a sudden we realized that something interesting was happening here. And if you look at it in more detail, we actually found that this outflow was accelerating. And so a little bit of fun last year was we did a little press release on this because there's been a lot of people looking for accelerating broad absorption lines, but they're very difficult to find when you only have a couple of epochs because they're also variable in strength and shape. This plot over here on the right shows all of our spectra. So each tiny row here is a spectrum. And so you can see they going down is kind of like moving forward in time. And the colors represent the flux received. So blue represents absorption features, red shows us emission features. And so as you move down this plot, you're watching this blue absorption feature, which shows up here, move off to the left. And it's moving by around 2 million miles per hour, 800 kilometers per second. So this is a very fast moving outflow, and it's increasing its speed by quite a bit. So we were able to detect this at very high confidence and also sort of dig down into the details of what's happening a little bit. And so so that was kind of fun for us to do this little press release on it. It was picked up by a whole bunch of online news sources because I think, you know, black hole winds are kind of a cool topic. But it was entertaining watching the like game of telephone going on with all of these press releases as it slowly got more and more like outlandish claims, and I was like, oh no. But yeah, so you know, we have this first like really solid, really cool detection of an accelerating broad absorption line, and so now we're going to be searching for acceleration in the rest of our quasars that we're monitoring. Again, of which there's expected to be, you know, 100, 200-ish total. So we have a lot of work to do on these broad absorption lines, as well as with reverberation mapping, which again is the main science goal. So yeah, so you know, to kind of sum this up, time variability, both of emission lines and of absorption lines, is a really powerful way that we can explore the inner regions of quasars and learn about the masses of black holes. And so the black hole mapper reverberation mapping project that I'm involved with is really creating this new data set that nobody's ever really had the likes of before, that we can do a whole lot with when we're talking about exploring quasars from in a wide variety of ways. So I will end there, and thank you, and I will take any questions.
Thanks. Yeah, I'll start off with one. About 10 minutes ago, you had some models of some blue colored and red colored dots, which I assume are blue shifts and red shifts of a broadline region. Wondered what sort of model was that? Was that kind of a physical model with black hole and accretion disk and a dust torus and all that, or was it something a little different?
So that one, I think, sorry, I'll scooch back here. This one probably. So what this is just a model where of the broadline region. So it doesn't include any other structures. The things that we include in the model. So each of these little particles is like considered to be like a broadline region gas cloud, essentially. So we imagine that the broadline region is like composed of just tiny little clouds of broadline region gas. Some of them are moving toward us. Those are shown as blue. Some of them are moving away from us. Most of them, it's kind of hard to tell in these images, but most of these end up being like thick disks. And so just depending on how we're looking at them from kind of an angle here. But these are side views. So they're sort of thick disks that sometimes have a little bit of like a conical structure, but sometimes are more like disks. In these models, though, we include like the black hole mass. We include like the angle that we're observing, like any asymmetric emission, things like that. But we're not really considering like dust torus or any other structures within the AGN other than the broadline region.
Okay. Right. I'm satisfied.
Thank you for the talk. I had a question regarding what is the difference between, say, physical processes that give rise to broadline region as compared with, say, continuum spectrum?
So the general idea is that the continuum is coming from the accretion disk itself, whereas the broadline region, the broad emission lines are coming from a region farther out where you have more discrete like clumps of gas that are not technically part of the accretion disk. They may be above it a little bit. They may be kind of like an extension of it, but they're not, they're sort of distinct from the actual disk itself. But it does tend to be also a thick disk. So the gas is still distributed in a disk. It's just sort of a separate structure from the disk.
Thank you.
Yeah.
Yeah, thank you for the talk. Looking at those beautiful spectra, it looks like there's a lot of potential information in them. Do you ever do overall attempts to model spectra from black holes integrating over the broad regions and the other parts of the phenomena. Compared to,
Sorry, what was that?
yeah, do you ever try and compare? Do you ever try and calculate a simulated spectra for the entire AGN and compare it to data?
I have not. There are people who do. So there's a very active theory component to AGN as well. There's a guy out at Caltech named Phil Hopkins who does a lot of this, where he's generating models of the broadline region and the broad absorption line regions as well, and seeing how that would look in spectra. But my role and my group tends to be taking the spectra and then trying to back out measurements from it rather than modeling them. But yeah, there are quite a few people who do that. Yeah.
Thank you.
Looks like a chat, yeah. I'll click that button.
Oh, sorry. Okay, hold on. Okay. Can you get UV, optical, infrared spectra from public servers for galaxies like SDSS, or are these proprietary data? So eventually all the SDSS data do go public. They're released after a few years. So right now, like the black hole mapper data are all proprietary, but next year we'll be doing a big data release where a lot of these data are made public. Previous iterations of SDSS have already been made public. So like the SDSS reverberation mapping project that stopped at 2020, all of those data are public now. So anybody can access them through SDSS's like Sky server. And a lot of these galaxies do have, like, if you know where to look, they do have archival, like ultraviolet, from various other surveys, like the Galax satellite, which did a UV survey. We have optical surveys like Pan-STARRS and the Zwicky Transient Factory. So you can get mostly photometry, occasionally spectra that are public for a lot of these, but you have to kind of go hunting for the right sources. But yeah, a lot of multi-wavelength data exist for these sources.
Some data archives are better organized than others. Like,
Yeah.
I think you can get all of Keck Telescope's data, but it's just as it comes, and no one, it's not indexed or anything.
Yeah, they've been doing better, especially with like NASA data, for example. So like all the Space Telescope data, you can now search from like a single query for like all observations that have been taken of a specific object, and it'll give it to you. But yeah, I mean, actually using those data can be a little less straightforward, but finding them is starting to get a little easier.
Okay. Well, one more question or 0 more questions? We're in the binary part of the question and answer session.
Sorry.
Yeah.
Let's see. So Jose said that, but these data is one single observation. Yeah. So I mean, so the reverberation mapping data are over the years. So most objects don't have time series data unless they were from a dedicated monitoring program. So there's very few objects that haven't been like singled out by researchers that have time series data like this. So you're right. Most of the data that you would find would not be like these data that we have.
Yeah, that is special. The data set is quite unique. Just spectroscopic monitoring. I'm a big fan of spectroscopic monitoring, but there's almost no instrument built for that.
Right. We just don't have a lot of time series monitoring programs that are spectroscopic. There's a lot of photometric programs that you can find, but very few spectroscopic. It takes.
Yeah, well, thank you so much for giving us a glimpse into that unique perspective.
Well, thank you for having me.
Thanks, Lisa.